First one, in the Bohr model of boron, how many electrons would be in the second energy level? So if we draw our Bohr model here, the first energy level, let me move this over a little bit. First energy level, you can hold 2 electrons. Stop. You can hold 2 electrons, up to 2 electrons, right? So if you look at boron, boron has an atomic number of 5. So that means you have 5 electrons. 2 can go in that first energy level. So you'd have 1, 2. So if you minus 2 from your 5, you have 3 electrons left over. Now the second energy level can hold up to 8 electrons. Remember how we determine the number that goes in each energy level is the formula 2n squared, where n would be the energy level you're talking about. So for the second, you would replace n with 2. 2 squared is 4. 4 times 2 will give you 8. Bless you. So then the 3 remaining electrons can then go in that second energy level. So the answer here is 3. Okay. In the Bohr model of sulfur, how many electrons be in the first energy level? 2. Now, this question, I technically could have just said, how many electrons be in the first energy level? Because unless you're hydrogen, the very first element, every single element is going to have 2 electrons in the first energy level. Because that's the maximum they can always hold. Even if you're a massive atom that has tons of electrons, that doesn't mean you can hold more than 2 electrons in that first energy level. Okay? All right. So 2 would be the answer here. In the Bohr model of magnesium, how many valence electrons would it have? I think so. I got that. Yeah, go ahead. It'd be 2. Now that one might be a little trickier. So let's draw the Bohr model of magnesium. So magnesium, find Mg. We have atomic number of 12. That means yeah. Question. Valence is think of a wedding veil. It's on the outside of the face. Valence electrons are the outermost electrons. So in the Bohr model, in the Bohr model, you got 12 electrons because that's the number of protons. 2 can go in that first energy level. So minus 2 from your 12 starting. You have 10 left over. Let's put our phones up, please. Let's make sure we're paying attention. Okay. You have 10 left over. 8 of those 10 can go in the second energy level. Okay, so minus 8 from your total. Now you have 2 left over. In that third energy level, remember you could hold up to 18. N is 3 here. 3 squared is 9. 9 times 2 is 18. So then I only need 2 left over though. So those 2 would go in that third energy level. Okay. So then valence electrons, you would look at the final energy level you filled in, and there's 1, 2 that are there. Okay. Are we filling these in? Everyone still with me? So the answer to 1 is 3, 2 is 2, 3 is 2. How many electrons are in the fifth energy level? Who thinks they got that? Yeah, go ahead. 50. Yes. Now, how you know that? 50, so fifth energy level of 50 electrons. 50. How you know that? 2n squared. Because I said the fifth energy level, n is 5 now. No. There can be up to 7 energy levels. Most of the atoms I have you draw are just wouldn't be bigger than 3. Wouldn't be bigger than this. That's just because it would just be too time consuming to draw these. But you technically can, you can go up to 7 rings. It would take a while to draw them, but you can do that. So n is 5. 5 squared is 25. 25 times 2, that's 50. Okay. So everybody got that filled on the formative? 3, 2, 2, 50. All right, and then we got our notes out. So get yourself to the second lesson in the notes packet, History of the Atomic Model. So make sure we're all there. And then start filling in the blanks on that slide. Okay, we're all there. We're filling in the blanks. See, a lot of people not filling in blanks. History of the atom. Okay, you with me?
Yes, sir.
All right. The beginning idea of the atom actually starts with one of the Greek philosophers named Democritus. So if you look here, I highlighted demo. Democritus gave us a demo of the atom. So here's what he thought of. He was like, hey, if I take a stone, and he imagined if I were to keep like breaking a stone into smaller and smaller pieces, what would I be left with? And he predicted that the stone would be made of these stone atoms, he called them. Like stone, like these little tiny stone particles. And then he thought, hey, a lion, if I were to like look at the fur of a lion and I keep like splitting it smaller and smaller and smaller, he thought you would get down to these like specific fur particles, these specific fur atoms. Now, that actually is pretty much right? And it's kind of what atoms are, right? You look at this table is made up of certain atoms. Now the difference here is this, like we have like a periodic table of elements. These elements are like Lego blocks where you can reuse them to build different things. In other words, you don't have specific table atoms or specific laptop atoms. So he thought you had like every single thing on Earth had its own specific kind of atom. So that's where he kind of was inaccurate with his view of how the world was set up. Okay. Anyways, before Democritus, like you had Aristotle. Aristotle was After the reason why, like you might be wondering, well then why didn't like that idea catch on? Well, Aristotle, you probably have heard of him to some degree. Aristotle came after Democritus, and everybody went like cuckoo for Cocoa Puffs over Aristotle, and they were like, Aristotle's a genius. Everything he said is accurate. And Aristotle kind of gave this idea of the four elements, like air, fire, earth, water. Avatar: The Last Airbender, you know? And so everybody was like, that is definitely how the world works. And so everybody just kind of like believed that for a while, until we were able to do more careful experiments and kind of rediscover this idea of atoms. But it's interesting that, back in BCE, you had Democritus. You basically said it correct, Are we good here? He also thought these atoms were indivisible, meaning you couldn't break them up into smaller things. We know that's not true. We know we can break up an atom into like the protons, neutrons, electrons, and then technically you can break protons, neutrons, electrons into even smaller particles. Chris, give me a second before we. Yeah, they're related to each other. I mean, splitting an atom in terms of like trying to release like a bomb or like trying to do like nuclear energy, but you can split up an atom to like study without it trying to do a giant explosion. Yeah, it's tricky to do that, but yeah, it is possible. Okay, so moving on to fast forwarding, like 2,000 years to John Dalton. And John Dalton kind of brought us back to this idea of Democritus, where he talked about these things called atoms, where all of life is made up of these, he said, indivisible and indestructible atoms, kind of like Democritus said. But a unique thing he added to us is this idea of them being these solid spheres. So this solid sphere model, in other words, stone, like Democritus said, like, hey, a stone would have stone atoms that would be kind of shaped and would look like a stone. Democritus said, no matter if it's like a stone or a table or the sun, everything is made up of ultimately is these spherical atoms. So that sphere shape. And he was correct in that. But the atoms do resemble these spheres. Now we know they're not solid, right? In fact, we know it's the opposite. Most of the atom is just this empty space where the electrons are at. But he at least kind of established this idea that we have a spherical shape. He then hypothesized that whenever you do reactions, that a reaction is just going to be a rearrangement of these atoms. And that's true. When we learn about reactions, you'll see that all you're doing in a reaction is you're just rearranging atoms to build something else. Kind of like you're playing with Legos. And then he then said there were different kinds of atoms. And so atoms of the same element, of the same type, they're going to have a similar property, size, and mass. And that is more or less true, right? Like atoms, like all calcium atoms, for example, are going to have more or less the same size, more or less the same mass, and they're going to more or less behave the same way. So how can you remember Dalton and the solid spheres? A ton. You are a ton if you are solid. You're like, wow, that person is just solid. They would probably weigh a ton if you don't think about it. I don't know. That's the best I can do here. I have a hard time with names, like, because names, like, how do I remember these people? So for each name, I try to give you kind of a way to remember it, perhaps. You know, some are better than others, but that's what I got for Dalton. All right, we still good here? Everyone's still filling in? All right, cool. Moving on, J.J. Thomson. So J.J. Thomson, he discovered the electron. So you want to remember that for Thomson, the electron. Now, he didn't call them electrons, he called them corpuscles, which is kind of a goofy sounding word. But here's how he discovered the electron. So you want to know this experiment. He did what is called the cathode ray tube experiment. Where here's the idea, it's pretty clever. He has a cathode ray tube where he would shoot these negatively charged particles. He knew they were negatively charged, but he didn't know they were electrons. Well, he didn't know, I'm sorry, let me back. He didn't know they were negatively charged. He just knew I can shoot a beam of particles. And he then shot that beam of particles through these oppositely charged plates. You have a positive charged plate, a negative charged plate, and he noticed that beam will bend towards the positive plate. So think about it. Opposites attract, right? So if that beam, whose charge you don't know, bends towards the positive plate, that would tell you that beam must then be negatively charged, right? Otherwise, it wouldn't be attracted to the positive plate. And so that's how he knew the electrons would be what we ended up calling electrons. That's how he knew these particles are negatively charged. Okay. So then building upon this idea of these negatively charged electrons, or corpuscles, what he called them, he developed what's called the plum pudding model of the atom. So we've established at this point that we have atoms, but we're trying to figure out, well, how is the atom built? Like, what makes up the atom, right? We know we have these negatively charged particles, so he hypothesized that most of the atom is positively charged. And then surrounding this positive charge are those negative charged particles he discovered that he called corpuscles, we call electrons, and that negative charge is evenly spaced throughout the positive charge. Okay? In other words, why it's called plum pudding is, anybody have plum pudding? I'm curious. You got any plum pudding fans in here? No. I think I've had one student, every time I ask, it's like one student. But apparently it was a big thing back in his day. The cake, like kind of like the actual, like, the main thing of the dish, the cake, that would be the positive charge. And then the electrons would be like the plums that are like evenly spaced throughout the plum pudding. Okay? So here's how you can remember that. J.J. Thomson, if you don't think about it, Thomson sounds like thumb. So J.J. Thomson, think of a plum pudding with a bunch of thumbs just all throughout it. That's just you know what I'm talking about. J.J. Thomson, yeah, say what you want, but I still have students come by and they're like, J.J. Thomson. Anyway, plum pudding. Plum pudding. Now, hey, we know this is not correct, because we know the electrons, they're not evenly spaced throughout the atom. We know the electrons are in these energy levels, you know, like we see in the Bohr model, right? Where some electrons, like fewer are in the lower ones, and then more electrons are in the outer energy levels. Okay. All right, we good here? We're still awake? Okay. On to the next one, Ernest Rutherford. So here's the idea of Rutherford. He's working 1871 to 1937. he's the one that established this idea of the nucleus, and specifically that the nucleus is positive. So he established nucleus exists, it's positive, and that it's tiny. And his experiment's really, really interesting. So what he did was he shot a bunch of alpha particles. You learn about alpha particles, right? Those helium nuclei, you know? All right, so he shot these alpha particles at a piece of gold foil, okay? And what he noticed was, hey, most of these alpha particles are just going right through the gold foil. But then every so often, one of those alpha particles would then bounce back and hit the sensor. Now, that shocked him. Why would that shock him? Like, why would that be so surprising? Just randomly happens. He compared it to shooting a bullet at a piece of tissue paper and the bullet bouncing back and hitting you. That's how unexpected this was. So why would that be so unexpected? Like, what does the experiment like reveal? They were weaker, sure. But think of it. Most all of them are going through, but then every so often one bounces back. So maybe a better question, why are they bouncing back? Why would a particle bounce back and most of them go through? Think of what we know about the atom now. Or understand the atom now. What is it, in other words, what is it hitting that would make it bounce back? The nucleus, yeah. So what this says, really, so stick with me here. Okay? What is causing the alpha particles to bounce back is them hitting the nucleus. Most of them travel through, so what that tells you is most of the atom is just empty space, where we know the electrons are at. But then every so often, you're going to hit that super dense nucleus, and then they bounce back. Okay? Anyways, here's how you can remember that. Back in my younger days, kind of like, I live in D.C., kind of run the streets of D.C., and I'd wear my gold chain like this, kind of go around, maybe go to some of the clubs. They call me Mr. Worldwide there with my gold chain. I am Mr. Who? I am Mr. Golly. So, I'm Mr. Black Ford, right? So Rutherford Ford, and he did the gold foil experiment. So think of me and my gold chain, and then Rutherford, gold foil.
It's like, can you imagine if you ran on this thing? Can you ask your gold chain so I can remember this?
Put like a cigarette on.
I might go DBS, full Johnny Dang, drills, chain,
Anyways, all right, moving on. Here's another slide. Here's another picture showing the Rutherford gold foil experiment. I won't dwell on it too long, but it's just kind of another. If you're having a hard time picturing the experiment, here's another way to look at it. So there's the beam of alpha particles. Do you have anything to fill on this slide? I think I left it off. So yeah, the beam of alpha particles. Again, most go through, but then every so often one bounces back because it's hitting that solid nucleus. All right, moving on to Niels Bohr. So we've learned about Bohr before. It's what we did last class with the Bohr model. So what Bohr did was we've established that the nucleus exists. It's positively charged. We've established that. Let's keep phones up, please. You got a new slide to write notes down? Hang with me here. We've established that we have electrons. We got to figure out how are these electrons placed compared to the nucleus. And what Bohr said was, hey, I think these electrons are scattered around the nucleus, but not randomly, but they occupy these energy levels. Okay? These distinct energy levels. In other words, he said they orbited the nucleus like the planets orbit the sun. So here, the nucleus would be like the sun, and then the planets would be like the electrons. Okay. Now, technically, this is not correct. Technically, the electrons are not just like orbiting in this like these fixed rings. technically they're more in these, the orbits are more these three-dimensional regions that these electrons occupy. We'll talk about that later on in the year, but for now, just know, you could think of it as like as them orbiting the nucleus. That's fine for now. We'll get into the details later on. But here's how you can remember that. Things are boring if you just stay on that same path, like the electrons are.
Oh.
It's pretty good, right? Okay, whatever. All right, last one. James, wait, we good here? We done writing down? James Chadwick. Okay, so James Chadwick discovered the neutrons. So if you've been paying attention so far, you've like, all right, we got the nucleus. We know it's positively charged. We got the electrons, negatively charged. They're outside the nucleus. But what about the neutrons? Well, Chadwick was the one that discovered the neutrons. So here's what he thought. He thought, hey, this neutron, it must be made of a proton and electron pair that would then cancel each other out. Because what he figured out was if you just if you add the mass of the protons and the electrons in the atom, it doesn't add up to the actual mass of the atom is. It would be like if you were to like weigh your backpack and it weighs 20 pounds, and then you like weigh each thing separately and it add up to like 10 pounds. You'd be like, where did that 10 extra pounds go? Obviously you're missing something here. So he had to figure out where is that extra mass coming from. That's where the neutrons come in. Now, he knew the particle couldn't have a charge because he would try shooting these neutrons through that charged plates, through a set of charged plates, and they didn't bend to one plate or to the other. But anyways, that's the neutron. That's how we explain that that kind of unknown mass that exists. All right, so here's how you can remember it. Chadwick discovered the neutrons. So hang with me here. Stick with me here. All right. Okay. Yeah. All right. Neutron. Talked about that with like beta decay. Bay. We talked about Bay with like beta decay. This is Chad from High School Musical.
My favorite thing.
Back in my day, that was like the heartthrob, like Chad. You know? Like everybody just loved Chad. So Chadwick, Chad, neutron. All right, we all get it. We're all on the same page.
This one isn't important, right?
That what?
This isn't important.
This is. I'm sorry, I didn't hear.
This is important, like very important.
I mean, you need like I'm gonna test you on like what did Chadwick discover?
Okay.
We got no neutrons.
Chadwick discovered neutrons.
Yes.
Neutron.
Yeah. All right. Let me stop the recording.
No, no, no.